All right, so we're ready to move on to the next section in Chapter 4, Section 4.2, which is on vectors in n dimensions. So this is a generalization of the vectors that we considered in 2 and 3 dimensions back in Chapter 3 to any number of variables. And the reason we're doing this here is we want to view n-dimensional vectors as being a special case of matrices. And so we introduced matrices in section 4.1. We went over those in the last couple of videos. And one of the kind of big shifts we'll do here, there's two shifts we're going to make. One is allowing for any number of variables. The other shift we're going to make is a shift in notation. So in chapter 3, we used angle brackets to denote our vectors, and so we had kind of this. So in chapter 3, we said, something like, maybe x, the vector x looks like maybe x1, x2, x3. In chapter 4, when we want to write that same vector, we're going to think of it as an n by 1 matrix, as a column vector, right? So it's a single column, some number of rows and only one column. So this would be a 3 by 1 matrix. And we'll see that this is going to be a useful notational shift for us, because it's going to allow us to use matrices to describe systems of equations, write systems in matrix form. It's going to allow us to talk about how matrices define functions that take vectors to other vectors. And so it's going to be a much more useful notation for us. We mentioned back in chapter 3 that the main advantage of the angle bracket notation is that it fits a little bit better on the page. Okay, so there are two types of vectors that we run into: row vectors, column vectors. Row vectors we don't see that much of. So a row vector would be something that looks like, say, maybe x equals x1, x2, down to, say, xn. Right, so it's a 1 by n matrix, right? One row, n columns. A column vector, maybe we'll call this guy y. You have several rows but only one column, so you have a y1, y2, down to, let's say, ym. Oh, I said n by 1 on the slide, so let's stick with n. N. Okay. So, of course, you can see that both of these give you the same information, right? If I gave you, so let's just make this as a note. If I gave you the vector x equal to, say, 2, 2 minus 1, 4, y equal to 2 minus 1, 4, well, these give me the exact same information, right? They give me the same three numbers, simply presented in different ways. And depending on the context, you may want to present these numbers in one way or another. But most of the time, we'll be dealing with column vectors. There are very few places where we want to deal with row vectors. In more advanced courses, you might think of row vectors as being somehow dual to column vectors, but that's far beyond what we would talk about in a course like 1410. Okay, all right. A few more examples. We could do say column vectors in let's say, let's do four-dimensional vectors. Why not? We could do, say, u equals 2 minus 1, 3, 4. V equals 0, 1, 0, 2, and so on. We could do rows in let's get really crazy, let's do R7, right? We could do x equals 1, 2, 4, 0, minus 5, 6, 1. There's 7 numbers, right? Y equals -1, 2, 0, 1, 3, 4, 2. Right? So there's no, There's nothing all that tricky here. It's simply a matter of either you take a bunch of numbers, you write them as rows, or you write them as columns, whichever way you want to do it. One more example. Let's say these are going to be in R3, right? 3 numbers. We'll do columns. We might do something like, let's say, A is going to be, they don't have to be integer entries. 2/3, 1 plus the square root of 2, 0. That's a perfectly good 3-dimensional vector. Right, we can put whatever we want in these guys. Any real numbers we can stick into these vectors. You can even put complex numbers in them if you want, but that's not something that we're going to spend very much time on. Okay, now, because these guys are special cases of matrices, they satisfy the same properties as matrices, and we saw these in the previous video, right? So we know that x plus y is the same thing as y plus x for any matrices, so in particular for any vectors. We've seen this before. We know that addition is associative. We know that there's a 0 vector, so x plus the 0 vector is going to be equal to equal to x, where our 0 vector, we know what the 0 vector looks like. The 0 vector looks like, if we're dealing with, well, here I've said vectors, but really I guess I should say, let's do column vectors, but it's equally true for row vectors. So 0 being the vector consisting entirely of zeros. Negatives, we know that negatives work. X plus minus x equals the 0 vector, and as usual, we know that minus x is just minus x1 down to minus xn. You just change the sign on each one of the entries. It's still true that if you multiply by the scalar 1, nothing happens. Scalar multiplication is associative. C times dx is the same thing as c dx. And we have 2 distributive properties, right? We know that if I do c times x plus y, that's cx plus cy. And if I do c plus d times x, that's equal to cx plus dx. Okay, so you have all the usual properties. These 8 properties, by the way, in sort of a more general context where these vectors, maybe they're column vectors, maybe they're row vectors, maybe they're matrices. There are other scenarios where these things apply. You might be dealing with, you could deal with functions, polynomials, there's all sorts of things. These 8 rules collectively are known as the vector space axioms. And there are lots of other sorts of sets that behave algebraically in the same way that row vectors and column vectors behave. And if you go on and you take a course like 3410, you will see this sort of general picture developed there. Okay, so as I mentioned, vector space, you have sort of any set of objects where you have an addition and you have a scalar multiplication and they obey these rules. So we've seen some examples, right? We know that this works for row vectors. We know that it works for column vectors. We know that it works in general for matrices of a given size, right? Other examples might be things like you could do something like this. You could do, say, we'll use this notation, P3 of R. The set of all polynomials of degree 3 or less, so things that look like a0 plus a1x plus a2x squared plus a3x cubed, where all of these a's are real numbers. That also works as an example of a vector space. You can play around with that and see that it works. You could consider, the set of all. You consider the set of all functions. maybe functions defined on maybe some interval AB, real valued functions defined on some interval. Lots of possibilities, but for us, the only real one that we are going to work with is the case of column vectors, and occasionally matrices. And if you want to consider vector spaces in general, you can study those in Math 3410 once you're done with this course. Okay, that's it for this. In the next couple of videos, we're going to be getting a little bit more abstract. We're going to be talking about some of the kind of inherent properties of vector spaces, things like subspaces, span, linear independence. These are concepts that a lot of students find kind of tricky. They are some of the more difficult concepts that we consider in this course, but they're concepts that we'll return to a number of times, and hopefully with repeated exposure, by the end of the course, you guys will have the hang of these things.